In this video, I'm going to discuss the famous machine learning publication, Attention is All You Need. This paper was published in 2017 by researchers at Google and has had a great influence on the modern innovations taking place in the machine learning landscape. I'll be going over snippets of the paper and the underlying components of the transformer architecture. So let's get straight into it. So before transformers, natural language processing tasks such as language translation relied heavily on recurrent neural networks and long short-term memory networks. These models process sequences one token at a time, so they weren't great at capturing long-distance dependencies between tokens within a sequence. This isn't great because even in our spoken language, we may have words placed in far apart, but may be critically related to one another, so they can have a significant impact on the overall meaning of a sentence. So this made RNNs and LSTMs look ineffective for performing language translation. And the fact that they were also very sequential in nature made these models difficult to perform parallel processing upon. So they became even more ineffective when working with large data sets or longer sequences. So to handle those problems, this paper proposes a new approach, which is to use a fully attention-based model called the transformer. And that would basically eliminate recurrence altogether. By leveraging self-attention, we can now process an entire sequence in parallel and basically scale faster and process faster so that we can work on more complex relationships. And this will basically reduce a lot of critical bottlenecks that we face when trying to perform sequence to sequence translations. So the transformer model right here contains mostly two parts, the encoder and the decoder. And those two parts are also broken down into more parts, but we'll start with these two. Each layer in the encoder and decoder is built mostly from two components, the multi-head self-attention layers and the feed-forward neural networks. There are also residual connections and layer normalization happening in there, and there are other factors that go into helping the model retain information and stabilize training. So let's get a look at the first part. So we're going to start with looking at self-attention. Self-attention is what allows the transformer to efficiently process sequences by allowing each token to focus on other relevant tokens in the sequence, regardless of their position. So every token in the sequence is mapped to three vectors: a query vector, a key vector, and a value vector. Each token's query is matched against the keys of all other tokens to determine a score that represents how much focus or attention one token should pay to another. Now, the attention weights are then applied to the value vectors, which actually carry the information content of each token. This mechanism ensures that the representation of each token is enriched by the most relevant parts of the sequence, and these scores are then scaled down by the square root of the dimension. This keeps the gradient stable and is later normalized using softmax and are finally adjusted and transformed into attention weights. Uh, these weights are then used to generate a weighted sum of the value vectors, and this effectively represents the token's understanding of the context around it. So this self-attention mechanism as a whole enables the model to capture dependencies between tokens, regardless of where they are in the sequence, and this is crucial to understanding the language nuances that may be present. By processing all the tokens simultaneously, we can also make our computations a lot more parallelizable, so this will lead to faster and more scalable training than we would have with an RNN. A little bit more about multi-headed attention now. So multi-headed attention takes what we learned about self-attention and takes it one step further. So instead of having just a single set of query, key, and value transformations, we have multiple sets that happen in parallel. These are called heads. Each head learns a unique pattern of dependencies within a sequence. So each of them have their own K, Q, and V values. So these will help provide different perspectives on the different perspectives on the input data. So for example, one head might focus on short range dependencies, one might focus on long distance dependencies or relationships. There may be heads to look at syntactic or even semantic patterns. They can do whatever basically. In practice, each attention head independently computes their own attention scores and outputs, which are then concatenated and passed through a final linear transformation. This allows for a more diverse combination of views within each layer and allows the model to learn more complex patterns than would be possible with a single attention head. So this improves the model's representational power and helps to understand a wider variety of nuanced relationships across tokens. So this flexibility is what allows us to use the transformer with a great performance across a variety of tasks. And this can be used to understand different kinds of contextual information a lot more quicker. Okay, now let's look at positional encodings. So since the transformer processes all the tokens in parallel, it lacks the natural sequence ordering found in models like RNNs or LSTMs. And this basically makes tokens in a sequence to a transformer look like a big bag of tokens. Like there's no sense of order present to it. So to address this, the authors included positional encodings to inject information back into the system about each token's position within the sequence. So positional encodings are added into the input embeddings, and they basically allow the model to distinguish tokens based on their positions. These tokens are designed to provide positional information that the model can learn from, and they usually follow a trigonometric function like a sine or cosine function, and they use these functions at different frequencies to generate these encodings. And the continuous pattern allows the model to generalize to longer sequences than it was initially trained on. So it captures these relative positions in a way that's invariant to sequence length. And then by adding these positional encodings to the embeddings, the model gains a sense of order, enabling it to understand the sequential relationship between the tokens. It's simple, but it works. And the transformer basically can preserve this information without relying on the sequential nature or recurrence of a sequence. So it's much more effective and parallelizable at the end of the day. Um, this is a diagram of a simple encoder decoder, and it's not as complex as the initial diagram you might have seen for the transformer architecture, but it captures the essence of the sequence to sequence task of translation. And in our transformer architecture, again, the encoder is responsible for reading and encoding the input sequence to a series of representations that capture the relationship and meaning behind the tokens. And then the encoded information serves as a foundation for generating the output sequence. Each encoder layer consists of those two main components, like we discussed, a multi-head self-attention mechanism and a feed-forward neural network with other kinds of components like residual connections and layer normalization to stabilize and enhance learning. The decoder will take that representation vector from our encoder and produce the output sequence step by step. And each layer has three parts in the decoder. So we have a masked multi-head attention mechanism, which basically allows the decoder to focus on prior tokens in the output sequence, and an encoder-decoder attention layer, which attends to the encoder's output and a feed-forward neural network. So the encoder-decoder attention lets the decoder look at relevant parts of the encoded input while generating its output token. This layered interaction between the decoder and encoder allows the model to generate the contextually rich output sequences that it wants. A little bit about performance now. So the transformer architecture offers great advantages when it comes to training and computational complexity because of how it relies on self-attention. So a lot of the power that this transformer architecture has is due to the fact that it relies on self-attention, and it, it's a lot better utilized when we're working with GPUs and TPUs. So from a computational perspective, the transformer's uh, self-attention complexity has a runtime complexity of n squared d, where n is the sequence length and d is the model dimensionality. In comparison, recurrent neural networks have a complexity of nd squared due to the fact that they process tokens one after another. And although the transformer self-attention is more costly per layer in terms of memory, the speedup from parallelization and elimination of recurrence makes it much more scalable for large data sets and long sequences. The paper also goes further along to mention that they use dropout for regularization and layer normalization to stabilize training. When those two are also put together, the transformer can easily outperform traditional models and do much better on sequence tasks with much less training time. So that's absolutely a win. Finally, let's just take a look at the impact and contributions this paper has. So No doubt that this paper has set the foundation for many state-of-the-art models that we see today. The introduction of attention and use of parallelization definitely paved the way for more faster and scalable models. Um, Models like BERT, GPT, and T5 have been setting benchmarks in tasks like language understanding and text generation, as well as translation, ever since. Beyond NLP, transformer architectures have been adapted for applications like computer vision, where we see its application in tools like vision transformers for image recognition, as well as in bioinformatics and reinforcement learning. Uh, of course, the core contributions have transformed how researchers and practitioners have approached sequence data. So there's a huge paradigm shift happening in deep learning, and the lasting impacts of these contributions will continue to play a role in the machine learning landscape. And for the next decade or so, it will continue to remain one of the most influential publications for the machine learning landscape. So yeah, it's pretty cool.